Hey everybody, we're gonna start our very last topic this semester. I want to do a little bit on AC circuits, and I think as hard as this is, but the reality of the situation is we're out of time. So as much as I would like to go through and uh, do a bunch of uh, analysis of AC circuits and show you how cool they really are. Um, well, I'm not going to do that. Sorry. Um, but I encourage you to find some questions from this and take them. If you are interested in more and more other things to do with this class and or things in greater detail, I highly encourage you to check in with Paul. Paul will be available throughout the month of January, I believe, and can certainly set up and hold regular meetings to discuss particular topics or extensions of topics or topics in greater detail or whatever makes sense. So um, So there's that. I talked to him and he can offer that. So the topic of AC circuits, I think I'll do a little bit on here and then I want to do a conclusion with Maxwell and kind of revisit the Maxwell equations, and I think that's going to have to do it. So here we go. I'm going to do a little bit on AC circuitry. So an AC circuit, already, is something that oscillates, right? It's an it's alternating current. So if I look at a graph, okay, of say the voltage versus time, I'll just call it E for the voltage. If I look at a voltage versus time of an AC current or an AC outlet or something like that, I would find that it would be something like this, where I'm trying to hit the peaks again. I'm trying to keep the troughs about the same size as the peaks. This is supposed to be a very good, symmetric, wonderful cosine looking curve. Okay. So that I could write this as E of t being some E naught times the cosine of omega t. Okay, that's my goal here. So the peak voltage is this. There are several different places to measure on the, well, actually, no, there's not. There's really only two. There's the peak voltage. I will just note this for informational purposes. You probably already know it. There is something called the RMS voltage, which is probably somewhere about here. Okay. So what is the RMS voltage? The RMS voltage is kind of an average. If you took the average of a cosine, you could see you'd get zero, right? It's as much above as it is below. So you can't do that. So what you have to do is you have to square it, take the average, and then square root it. In other words, you have to take a root of the mean of the square. Square it first to get rid of the negative bits. Take the average or the mean, square, mean, and then square root it, root, mean, square. So the RMS voltage out of a plug is 120 volts. The peak voltage out of one of the outlet plugs is more like 140. Okay, so there's a difference. When we talk about 120 volts coming out of the plug, that's the RMS voltage. That's what your voltmeter will probably read, because when it's AC, that's the easiest thing to read, is the RMS voltage. So what's nice is we like to represent this in a what's called a phasor diagram. We like to I think, and so I guess do lots of other people, that phasors are great because it prevents you from having to do all this crazy trigonometric identity adding. What if I wanted to add a cosine to another cosine with a different frequency? Or what if I wanted to add a sine to a cosine or something like that? You got to go look up all these blasted trig identities for the adding formulas and all that stuff. But if you use phasors, it's just like adding vectors, and it makes the whole process much easier, at least in my opinion. You'll notice that a cosine, you probably ran into this in 4A. A cosine is the function for an oscillating mass spring system, right? You just bounce, 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 or if it's this way, bounce, 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 bounce. So you can do a phasor. I don't know if you did this in 4A, probably not, because there just isn't very much time for that kind of stuff. But here's what I call the phasor. Phasor, in case you've never heard of phasors, insert whatever Star Trek joke you would like to at this point. Set to stun. Okay. A phasor is actually stands for the phase vector. In other words, it's a vector that maps the phase of the oscillation. Okay. So what we do is you say, okay, look, I like to start with a cosine. The reason is because when I make my unit circle, ooh, well, a little bit of a unit egg, but that's okay. Whoops. Okay, get it through. Okay, good. X, Y. If you remember the unit circle, the one that you learned in trigonometry with the cosines and the sines and pi over 4 and pi over 6 and pi over 3 and all this kind of stuff, that's actually useful. Okay, so here is a way to think of a phasor. A phasor is basically a rotating vector. Okay, it rotates at the frequency of the wave, the omega frequency, not the natural frequency, not the f. Its tip makes the circle; it just goes around, and its projection onto the x-axis is essentially the value of where you are on the cosine curve or the oscillating or sine if it's that, right? If it's a cosine, then I started right here at t equals 0, right? If it's a cosine like it is up here. Why? Because that's the amplitude, that's the maximum, the voltage that I can get, and this is the maximum along the along the x-axis. You know, it's so funny. I'm kind of thinking, oh, I can't write over this. It's like having whiteboard markers and you're going to have a red over a black. No, I forget that. It's not that what happens. So at t equals 0, that's the maximum amplitude in the x direction. So that's where a cosine would start. Then as we come up to this thing and we drop down here to this point, how much is projected along the x-axis? Well, 0, because I'm on the 0. And the value, right, the value of where you are on this wave is the projection of this phasor onto the x-axis. So I need a point where it projects 0. Well, that's going to be right here. Oops. Ooh, right there. Okay. In fact, what I'm going to do is I'm going to do this. Right here at the very start. I'll do it right here. Right here at the very start. Here's the circle, and that's the direction of your phasor. Okay, right here at the first 90 degrees, your phasor is pointed straight up at 90 degrees. Now you're down here at -1 that way. Now I'm back up here at a 0 again, but this time the 0 is that one, and back up to the full peak, back to there. So this is it's just like a clock going around counterclockwise. So that goes to this one, this goes to this one, this goes to this one, and this goes to that one. And then it repeats itself, right? So the phasor swings around the tip of the circle, right? The tip of the phasor swings around the circle, and it goes around and around and around. And by its angle, you know where you are on that cosine curve, right? So if I take this phasor right here, ding, like that, well, there's an angle here, theta, and I know that that's between 0 and 90. Maybe it's like 40 degrees. Okay, well, I'm going to be somewhere about here, right, on the thing then. Look at my projection. My projection onto the x-axis is not as big as the full amplitude, so it's dropped a little bit, but it's not 0 yet, okay? So this point here corresponds to this amount right here. All sorts of good things happen with this, okay? So this is how a phasor works. The reason is because you can write the projection of this point as it travels along the x-axis, right? Here and then back to 0 and then back to here. That is simple harmonic motion. Near, near, near. Just that tip. If you were looking only at the projection onto the x-axis, right? It's as if you had a meter stick and you were shining a light and you looked at the shadow, right? The meter stick is full when it's horizontal, and then it comes up to vertical, and now it doesn't make any shadow at all. Now it's this way, so it's pointing there, and now it's back this way. If you're looking at the shadow goes big to 0 to big the other way to 0 to big the other way to 0 to big the other way to 0. That's simple harmonic motion, and that's described by a cosine or a sine, if you like. Okay. So the projection is the instantaneous voltage in the circuit. It's the instantaneous voltage supplied by the power supply, by the power supply. Yeah, it's the instantaneous voltage. So the projection, this projection, instantaneous voltage supplied. In this case, I'm talking about a power supply, but it'll be true in general, whether it's a resistor, a capacitor, or an inductor. That projection is the instantaneous voltage across that element. It's instantaneous at that instant. Good, nice one. Okay. Okay, so what I want to do is take a look at a circuit now. Okay, a circuit with an AC source. Oh, no, it stopped moving. And it's going to go real soon. Okay, a circuit with an AC source. Let's just make it resistive. So I have only an AC source, an AC power source, and a resistor. So here's my AC power source, and here's my resistor. Okay, so that's going to take the place of my cell battery, right? This is now the power source. And I'm going to call that E, which is a function of T. Okay, so it's supplying AC current to this thing. And the current is, right, the voltage is flipping back and forth as it goes, and therefore the current is winding back and forth, up, down, whatever. Okay, so at one instant, the current's going that way. At the next instant, it's going the other way. Since the current is now time dependent, I'd like to call it small I. And if I were to connect a voltmeter across this thing here, I would read a delta V across this resistor. Actually, delta VR. Darn, I didn't leave enough room for that. What I mean by that is delta VR. I just erased that. Okay, so there's an instantaneous voltage that's changing across the resistor, which I'm going to call little v now. So what I'm going to do is I'm going to leave capital quantities like we have been using I for the current. I'm going to call that now the peak current. And I'm going to call delta V with the bars on it the peak voltage. and I'm going to make little I and little v the instantaneous quantities, so that if I were to say, what's the voltage across the resistor? Well, it turns out that even in ACs, energy conservation still holds, right? Shouldn't be broken just because it's an AC circuit. Therefore, KVL is still a thing we can use. In this situation, if I loop around here and I write the voltage of this power source and I write minus the voltage of the resistor, those two things have to be equal. So what I could write is delta VR, which is a function of time, is equal to the peak current, the peak voltage, delta capital VR, right? That's now the biggest that it can be. For example, if I do the same thing as over here, and I use that for the input voltage, then I'll find that this is a cosine of omega t. Wonderful. You stinker. All right, well, not everything's perfect. Okay, so cosine omega t. And likewise, the current in the circuit, I, as a function of t, would be capital I cos omega t. Because I'm using capital I as the peak current. So and I forgot to tell you, this is resistor R. So what's the relationship here? Well, still, right, that's still true. They're in phase because the voltage and the current should be peaking at the same time, which essentially means that, come on, move. That if I graphed both the voltage of the resistor and the current of the through the resistor at the same time, they would both lie on top of each other. They would both be cosines. So suppose that I do that, and I'm going to do, nope. I'm going to do the voltage in red, say, or yeah, sure, I'll do the voltage in red. Oh. Okay, I'll do the voltage in red, and I'll do the current in blue. So the voltage, say, is, right, AC voltage, and the current, I mean, it would be delta V divided by R. So suppose that R is, 10 or 5 or 2 or something like that, but it's going to be less, right? So the current is going to be slightly lower, but it's still going to do the exact same behavior as the voltage. So it's going to look like this. Whoa. Oh, man. Okay, sorry, that did not work out at all. Let's try that again. Oops, missed that last zero there. Sorry, it's supposed to be right on top of the zeros are supposed to coincide. Close enough for government work. Okay, look, they're peaking at the same time, right? Their troughs are at the same time, their zeros are at the same time. So the voltage divided by the resistance is the current. And we still have a version of Ohm's rule available to us in AC circuits. Okay, just make sure you're using, well, look, we're not really going to do a bunch of calculations. This is mostly going to be qualitative. Okay. And like I said, if you want to learn a little bit more about this, Paul is available after the class. We just don't have time to go through it. Okay, so we're here. Oh, so wait, go back. I got to draw a phasor diagram. What am I doing? Okay, I don't like that one. Can I change that to that one? That one's nicer. Oh, gosh. Wonderful. Okay. Okay, so let's draw a phasor diagram. Red was the voltage. So I'll pick a spot. I always typically pick something about 40 degrees so you can see it in the first quadrant. But as you know, that's going to be a spot that's right about. Why do I even bother trying to do stuff on this thing? Okay. All right. It's okay. Just a little bit of time left until we have to do it all again in the next semester. Look, if I take that spot and I take that same angle here, I'm going to go on the same angle right there. All right. So where are those things? Okay. So they're going to be, say about past 40 degrees, 45, 40, like that. They'll be like this. Ding, right? There's delta V. That's going to be delta VR. Well, actually, okay, this is the peak. This is the peak voltage. And then the actual value of the voltage as given by this graph, if I were to go read this value, that would be, right? This distance right here. That's delta little v. At that particular instant, that's delta little v. The peak doesn't change. It's the size of the radius, right? The peak doesn't change. It goes all the way around the circle, the tip of it. So that's the peak voltage, is the entire size of that arrow. But when you project it down onto the x-axis, that's the size of the instantaneous voltage that is occurring across the resistor at that point in time. Okay? So that's where the cosine bit comes in, right? That's delta VR. Look at the triangle. It's delta VR times cosine of theta. It's that side. Don't you love the unit circle? Well, maybe not, but maybe you will soon. Okay, look, the current has the same exact phase, just lower in magnitude. It's going to be there. And then I don't want to overwrite the whole projection thing onto the x-axis because that's going to mess up the delta VR ping. But the same thing would be true if I projected it down onto the x-axis. Capital I times the cosine, which gives you the adjacent side, would give you the instantaneous current running through the resistor at that point. Okay. So the current in the circuit is always in phase with the voltage across the resistor. Okay, so that's important because the phases of things are going to be pretty important here. What this tells you is that current is always in phase with voltage, with the voltage. The voltage. I guess I should say across the resistor. I was going to say of the resistor, but voltage across the resistor. That's funny. That looks like resistor. Resistor. Okay. So that's something we can take to the bank. Every time we have a resistor in the circuit, in an AC circuit, and we want to measure the current, we can just measure the voltage across it and divide by R. Okay, because that'll give us what the current is in the circuit at that point. So the voltages, we're going to really concentrate on the voltages, and we're going to just note that the current is in phase with the voltage. So it's the same phasor as the voltage across the resistor, just reduced by the resistance, just as Ohm's rule would tell us. Oops. All right, so delta V equals IR, like so. All right, all instantaneous quantities. Okay. All right. Okay. This is going to be, I don't want this to be brutal. I just want this to be just, you just started laughing, didn't you? I want, I want this to be an easy picture drawing way. I should have said this at the beginning. I was thinking it, but I didn't say it. This is you know how I am with pictures. This is the picture introduction to AC circuits. We're not going to do calculations really, but I want to at least show you the conceptual underpinnings and show you the pictures involved. Okay, so I'm going to move on to a capacitor now. All right, so capacitor in an AC circuit. Look, I can't just put one single capacitor by itself. I want to have a resistor in there so I can measure the current. Okay, so it really needs to be an RC circuit. Come on, move. Thank you. So what I'm going to do is I'm going to throw in a resistor, pop a capacitor in here, and stick it across an AC power source. Okay. And this is my C. And the voltage across the capacitor is the voltage across the capacitor. So this is going to be kind of interesting. Okay. So KVL still holds. So if I loop around, I would have said E, right? This is a function of time, right? This is E as a function of time minus delta VR minus delta VC should equal 0, right? Those are the instantaneous quantities. Okay. And I'm just going to assume for a minute that I put minus delta VC. I'm just going to assume for a minute that current is going in the same type of direction. It's kind of going this way. And that I am building up a, I'm supposing that I'm building up a charge on the capacitor. Okay. So I'm going to get a delta V across there. Right. So I'm just assuming I'm going to get a plus with a minus right here. All right. Okay. Let's take a look at what this means. Notice that these are instantaneous quantities, not peak quantities anymore. All right. That you can't do anymore. Okay. So suppose that I have this. I'm going to look at the voltage. I'm going to look at the voltages here. So I'm going to have E, whatever it is, minus IR minus Q over C equal to 0. Okay, so you can see that the same thing is essentially happening, and Q is the instantaneous charge on the capacitor. You can see the same things happening as it did before with the capacitor, right? So what we did before was we just looked at an RC circuit where I charged the capacitor up a little bit and then unhooked the battery and discharged it through a resistor, okay, or like a light bulb, made the light bulb come on. So what I can do in this case is take a look at what these voltages are doing. Okay, you know already that the Q, no, you know already that I is dq dt. Okay. So what's happening here physically is the power source is pushing current, say clockwise. That current is hitting the capacitor plate and building up charge on it. The power source is going to slowly lessen its push, but still keep pushing. It's going to push really hard, and then it's going to push less hard and less hard and less hard, and eventually stop pushing. At which point the charge on the capacitor is going to be essentially as big as it could possibly be. Okay. The power source is then going to reverse the current, and the charge is then going to start coming off the capacitor. But notice that there's a lag now. If you think of the charge on the capacitor was at its peak when the voltage of the source was 0. Okay. Now what's going to happen is the power source is going to discharge the capacitor, right? The capacitor is going to start pushing, and the charge is going to start coming off the capacitor. And at some point it's going to reach 0. okay? And the capacitor is then going to charge oppositely the other way. The current's going to be running counterclockwise, and now it's going to charge the bottom plate positive. So the charge on the capacitor is oscillating also, but it's not in phase with the voltage of the source, is it? Because so note that if I draw, I'm just going to do this quickly. If I draw, let's do this in red, the E, okay, and I say E is going like this, okay, and I'm going to do Q on the capacitor in blue here. So what's happening now? Initially starting with an uncharged capacitor, the voltage is on and going, and then suddenly kicks off. Well, once it starts pushing the voltage, once the voltage flips and it starts pushing current the other way, that's going to start removing charge from the capacitor plates. Okay, right? Because look, if I go back over to this thing, if current was going clockwise and then suddenly the voltage went to 0 and started going counterclockwise, now the positive charge is leaving that plate and going onto the bottom plate. Okay, which means that the charge of the capacitor started at 0 and became a peak right there. Now, after some amount of time of the voltage being the other way and the current running in the other direction, it's now taken all the charge off the positive plate and it's put it on the bottom plate. But that's where all the negative was, so it's zeroed out the capacitor. Okay, and now it overshoots and it says, okay, I'm going to keep putting positive charge. I'm doing it at a lower decreasing rate though. I'm taking positive charge off the top plate, putting it on the bottom plate. So the bottom plate becomes positively charged and the top plate is negatively charged. And it reaches a peak. And then the voltage flips again. And then you can see, okay, yeah, about like that. Well, that was a little bit short, but you see, these are not in phase anymore. So the voltage across the capacitor and the voltage across the source are out of phase. This is very difficult to comprehend sometimes, okay? Which is why we have our phasor diagrams. Let's do this as a phasor diagram because they're lovely. All this stuff with you see how adding all of this to this is going to get really trigonometrically disgusting, right? Let's do some phasor diagrams. I'm going to do this one. I think then I'm going to call it good. So I just made a qualitative argument right there. I think you can see it though. Oh, real quick, I'll just throw in a little bit of math justification for that. I think you can see it because you remember how the current depended on the cosine? It was the same as the voltage across the resistor. Look, the charge is going to be d by dt of that cosine, a sine, right? If I differentiate the cosine, I'm going to get a sine. So the charge on the capacitor is going as a sine, which means the voltage on the capacitor is going as a sine, right? So if that's a oh, my hand is too cold. Cos omega t, then this becomes something like a sine omega t. I know there's minuses and whatnot involved, but never mind that. Okay, sine omega t. But notice that the voltage across the capacitor is proportional to the charge, which means that delta VC is proportional to sine omega t, just like the charge is. Okay, so the voltage across the cap is out of phase with the voltage on the source. Here is your phasor diagram. Okay. I'm gonna warm the hand up a little bit here. Okay. Okay. So when the source, which is in red, I'll put this up at an angle here like I always do. That's E. So the source voltage is, well, I should be a little careful with this, shouldn't I? I was talking about the current, so I should be careful with this. That's not technically E. That's not technically E. That's the voltage. This is delta VR. Because I'm talking about the current. I'm talking about the current going this way and the current going that way. So remember that the current is lined up with the voltage across the resistor. So that's how you can measure the current. So I'm really talking about that. I'm not talking about the source voltage. I'm talking about the current in the circuit. Okay, I'm sorry. I should be more careful with that. So this is really delta VR, which is the same phase as I. Okay, so I'm going to tell you that I is in there as well. All right, but as the current goes this way and then starts going back the other way, it starts to discharge the capacitor. That means the capacitor voltage was at its peak, which means that if we take a look, where does it reach its peak? Well, in time, which one peaked first? Because whichever one peaked first was the one that crossed the x-axis, right? Going this way, right? So if the voltage of the resistor peaks first, it hits there. But look where is the blue voltage of the capacitor? It's down here. It has not peaked yet. It's got 90 degrees to go before it peaks. So there should be a 90-degree angle here. Well, this doesn't necessarily have to be the same size. So maybe I should just be a little more careful with that too. I probably shouldn't be making these the same size. The reason being that, let's back this down. Come on. I don't know. Reason being that okay, there we go. Well, the reason being that the entire voltage, they're gonna need to add to a particular amount. So you make the voltage of the capacitor like this. All right, that's delta VC now. Okay, so it's 90 degrees out of phase. That's a 90-degree angle because when the current was peaking, I drew E. I did this all by. I'm sorry. I kind of misled you there. Sorry about that. But I was talking about the current, and I should have been talking about the current rather than the source voltage. So this, let me change because this shouldn't be that. Let's do I. There we go. So I in the circuit is high, and it starts building the charge up on the capacitor. I kept saying voltage. Sorry about that. So the current in the circuit is high, builds charge up on the capacitor. The capacitor eventually peaks in charge, at which point the current stops and reverses, which then takes charge off the capacitor. Therefore, the voltage of the capacitor, which is related to the charge, is 90 degrees behind the current. Okay. And we have a little mnemonic for that. And that is that for a capacitor, current leads voltage. So it's ice for a capacitor. Current should be in front, right? Capacitor, current in front of voltage, I in front of E. E being delta V in this case, but you can't say delta V because then that won't make a nice word. ICV is not a nice word. Ice is an easy word to remember. So I comes before E, the voltage in the C. All righty. Okay, that's going to take a little while to process. So I'm going to stop here, and in the next video, we'll go through inductance in the AC circuit, and then we'll try to put them all together and see where we go. It's going to be fun. But like I said, this is conceptual only. I'm not going to do any calculations. I'm not going to do any examples, and I'm not going to ask any of that from you. I just want to introduce to you the behaviors of these circuit elements, the resistor, capacitor, and inductor in an AC setting. So that's what we're doing. And then tomorrow we'll do some Maxwell equations, and then that's going to be that. And then this pesky final thing. All right. Happy day, happy time. I'll see you soon.